Thank you very much for that kind introduction. First time in Estonia. I hope I can live up to the expectations of what Uber said. In this lecture, we are going to have an interactive session. So at one point, you will need to get out your phones or your laptops because I will be asking questions. And there will be also an exam, okay? So you will be tested on the knowledge that I will be delivering, just to see. You can use ChatGPT if you want. Okay, so let's see now. This works really well in my laptop. Let's see if I can make it work here. VBox. I'm going to start a poll. See, present full screen. So if you just get that QR code, or you go to vbox.app and type in the ID that you see there, 122362420, you should be able to go to that poll. And I want to start with a couple of questions first, and then I will go with the presentation. So let me just see. Oh, yeah, many of you are connected. So the first question is I want to get to know my audience, right? I'm going to teach this topic, so I want to know first how much do you know about it, or perhaps you have not even heard the term. Let's see. There. 28 out of 34. Most of you have not heard the topic. Some of you a little bit. That's giving me an idea. Okay, so now all of you have answered. Now I know my audience. And I want to know your knowledge about the history of communications. Okay, so the next question is, okay, hold on, let me stop this.
As you would expect, it's a light, a desk lamp. And you could put your book beneath and could read. It's illuminating the space. But at the same time, you see this.
When do you think it was the first time that voice was transmitted over light? This is what I mean. Right now, you talk on your phone, and then magically, that voice is transformed into radio waves that they convey the information. That can also be done with light. So you can put your voice on a device, and then light transmits that data. When do you think it was the first time that a human was able to transmit that data? Okay, so I don't want to bias the answers. I'm not going to show the results now, but let's just see where you are. 26, 28 out of 37. Okay. We're almost there. There's 2 left, so let me show the results. Late 1800s, 33%, 35. Most of you think mid-1900s. Okay, this already is giving me an idea. And now let me just go back to the presentation. Oh, sorry. So those were the first 2 questions that I asked, and there are going to be a few more throughout this session. So this story is going to be about the history of communication and sensing with light. And what I want to do is I want to give you some tools. So by the end of these lectures, hopefully even the people that didn't know anything about this could buy, if they want, with 20 or 30 euros, the component to develop your own link. Okay, so that's going to be the idea. For the motivation, I'm not sure how many of you have seen this TED Talk, but visible light communication has been there for some time. I hope that sounds going to be okay.
And localized as a promotion for people.
Philips LED fixtures that are installed in the store use VLC technology, visible light communication. Each luminaire sends out a unique code that can be directly detected by any smart devices using a camera without any additional device or accessory.
Philips LED light.
Could read. It's illuminating the space. But at the same time, you see this video coming up here. And this is a video, high-definition video, that is transmitted through that light beam. You're all critical. You say, this is a smart academic doing a little bit of tricks here. But let me do this. Once again, still don't believe?
Okay, so that talk was in 2012 by Professor Harald Haas, who was one of the pioneers in visible light communication. And I guess during the next hour or so, I will teach you the basic techniques that you can implement, even if you have no knowledge on electrical engineering, to build your own link. There he was transmitting high definition video with the techniques that I will be showing you. You will not be able to do that. That requires megabits, but you will be able to transmit a standard definition video. Okay, so that's part of what we are going to cover. But you can also do sensing. And in this case, let me show you a system that was developed by Philips for localization. So as you know, GPS works really well outdoors, but once you are indoors, I'm not sure if you have tried to localize yourself. It just doesn't work. Why? Because the signals that are coming from the satellites hit our ceilings and they just go crazy. But you could see your lights as internal GPS satellites, and they can give you very accurate localization. So here, this is something that was deployed at a supermarket in France.
And localize the promotion for people.
Philips LED fixtures that are installed in the store use VLC technology, visible light communication. Each luminaire sends out a unique code that can be directly detected by any smart devices using a camera without any additional device or accessory.
Philips LED light.
So what that light is doing is just sending messages like GPS satellites, and then you can localize yourself in a supermarket and start doing different things. And on the part of sensing, I will tell you roughly how that system works when you have a light communicating with a camera, not a light with a photodiode. Okay, so that's what we are going to be talking about. Now, what is the basics of visible light communication? The idea is very simple. It's the same concept as if you would have a friend. Let's say that you're at night at the beach, and you have a flashlight, and you want to talk to your friend. You want to send a Morse code. You just turn the light on and off, right? Now, if you do that very fast, the human eye will see a normal light, but a photodiode will be able to see data. And that's just at the basics what is going on. So now a little bit of history. Or some other applications. This is not where it ends.
Here's a neat way of transmitting
I had a
sound
master
using
student,
sunlight.
and I was teaching this course at TU Delft.
It's called Series.
And he went and joined a consulting company, and then he said, "Hey, Marco, that consulting company is really nice because when you go to a room, you do not have any buttons to control the temperature. You just go to any room, you get your phone out, then the light is sending you a message. It tells you where you are, so everything can be controlled directly from your phone. So things like ventilation and heating can be controlled with visible light communication." Disney Research tried to create a new generation of toys.
I turn
the
on
one
the
that you see
amplifier.
there is if you have a magic wand, then that light is modulating information, and depending on where you connect with the dress of the little girl that is there, it will explode in different patterns. Cars as well, they can start modulating their lights to transmit data.
Notice
so
what
that's the
happens
key
when I block the
concept.
light from the transmitter.
Now, history. So light
How
is
does
what
it
we
work?
have been using as
Sunlight
humans to
reflects
communicate
off the mirror
wirelessly
and
for
goes to
hundreds
the
of
solar
years.
cell in the
Right?
receiver
You see
box.
just the fires that
But
we
the
were
speaker that
having,
the mirrors
and even now is the last way in which ships can communicate with each other if everything fails. So they just start blocking, like you see there. Sunlight was also used for communication, heliographs, just mirrors, and that was used by the armies even until the 1980s. So wireless communication with light has been there for some time. And this is the answer to the second question that you had. But what happened in the 1880s? In the 1880s, there was something called the photophone. It was a system developed by Alexander Graham Bell, the same person just developed the phone. And the basic idea was the following. So you have sunlight, and then sunlight was being concentrated into a megaphone, so it reflected information, and then information traveled to a very basic photodiode, which is made of selenium. And that was called the photophone. Now, you can create that if you want. There are many of YouTube videos that will show you that. This is just one such example. Let me just go.
Hi, gang. Here's a neat way of transmitting sound using sunlight.
Okay, let me just...
It's called Series to filter out unwanted DC from the solar cell. Back at the transmitter, I adjust the speaker and mirror to reflect the sunlight to the solar cell in the receiver's box.
So here they have a speaker reflecting light, and on the other side they have just a solar panel that is going to act as a receiver. And you will see that the music is being transmitted.
I turn on the amplifier.
Doesn't sound so well, but there's music in there.
Notice what happens when I block the light from the transmitter. How does it work? Sunlight reflects off the mirror and goes to the solar cell in the receiver box. But the speaker that the mirrors
And this is something that you can build. It's not so easy. You just get a normal radio with your analog signal, you open it up, you get your cables, you put it on your speaker, you start transmitting that information, and you have a relatively simple receiver and filter on the other side. Now, Alexander Graham Bell did something like this in the 1880s. And in a letter that he sent to his father, he said the quote that you have there, that he has been able to hear articulate speech produced by sunlight. So I heard the ray of the sun laugh, cough, and sing. So you can only imagine in the 1880s, him being able to transfer his voice, right, from one place to the other, just embedded in sunlight. And there will be a little bit of that topic that we will be covering that too. So what happens? Light was good, and it was the way in which we communicated wirelessly. Radio happened. So Marconi came with this wonderful experiment of transmitting information with radio waves. And we kind of stopped using light because radio has multiple good properties, like going through a wall. Light cannot go through a wall. And radio frequency is a great technology, but it faces a key challenge: bandwidth. So what's going on? If you see a little bit of the history of how we have been communicating, there's a before and after on this sound. I see some people laughing. It means maybe you're kind of old, like I am, because that's what we use, right, to communicate information before. So until the 2000s, there was only, by the time that that sound was there, only 5% of the world was connected to the internet. The connection was wires, and the data rates were very low, 50 kilobits per second. Now, more than 60% of the world is connected to the internet. The communication is mainly wireless, and we have tens of megabits being transmitted that we are requiring. On top of that, we have the Internet of Things. So all these radio waves that are there are getting super saturated. And what happens when there's a lot of demand for something? It just starts getting expensive. So we need to find ways to do that. Now I have a question for you. It's going to be question number 3. Link capacity is data rate, so how much data we can transmit from one point to the other. How many of you are electrical engineers or have done a minor? Or no? Okay, so this is going to be tough one, so at least one good answer will come from this question. You have a system that is transmitting data. And then somebody comes and tells you, I will give you 2 options. You can double the bandwidth, okay, so more bandwidth, or you can double the power. Double the bandwidth is like speaking faster, okay, 2 times faster, and doubling the power is like speaking louder. So which one of those 2 would be better to increase the amount of information that you are transmitting? That's the question. If one of them is better, if neither is good, or if both of them are important. So let's just go and see, test your knowledge on that. Okay, we have almost all of you answering. Okay, let's show the results. Bandwidth, great. That's the right answer. And the other ones, well, not so good, they increase data rate. And now let's just go back then to the presentation. So what happens? This is just the allocation of the spectrum for the United States. The EU, Estonia, we have something like that. And it's very crowded. So we will not go into the details of the equation, but there you see a C, which is capacity, how much data we can send. You see a B, which is bandwidth. This is kind of speaking faster. And then you see an S over N, which is just the signal over noise ratio, which just kind of reflects how loud we are speaking. So you can see that the B is linear. If you do 2 times B, you get 2 times C. But if you start doubling the power, S, you only get a logarithmic improvement. But what happens? Now we want more and more and more communication. And this is the problem that is causing. So did you see what happened now? Something changed in that slide. Did you notice the change? No? Okay, I will do it again. Do you see the change? Okay, now you see it. That little piece there of the spectrum, it was the C-band in the US. And a few years ago, it was auctioned. And people, well, the companies that formed the consortium paid 81 billion. Just so you have an idea of the amount of money that is, at that time, you could buy the 200 most profitable company, or the market capitalization, the 200 most expensive company, or you could buy the 3 most profitable airlines and still have cash left. And that's just for a little piece of air, so we can keep on transmitting our data. Our demand is so high that the price of that is increasing, of that bandwidth, because it's the easiest way to improve the data. So researchers said, well, we have the bandwidth for the spectrum for radio, and the electromagnetic spectrum for light, the spectrum for light is just a sister band that is on the side, so why don't we exploit it? Radio is just getting very crowded with cellular transmission, LoRa, Bluetooth, you name it. Everything is just relying on that pillar. Light on the other side is empty and it's free. So you don't need to pay all those billions to try to get it. And as I was mentioning before, the human eye sees the normal light that you see there, but we are encoding information. Now you can buy these systems, by the way. Huh? They are expensive, but you can buy them. You can buy some lights, you can put it in your desk at night, and that will be transmitting internet data to you in the same way that now we are getting Wi-Fi information. What are some of the advantages? If you see the spectrum of radio is very narrow compared to light, so we can exploit it. And now I would like to ask another question, because it's going to be an important component for our story. What type of LED was the hardest to create? So we have red, green, and blue. Let's see which one was. This is more like a sort of general knowledge. Okay, so almost there. Let's just wait a bit more time. And now they show the results. Oops. Red, green, blue, all of them were hard to create. Good, so the answer is the blue LED. So most of you, half of you got it right. So what happened? What happened was the radio was very good, and then we realized that we need more bandwidth. And some of you may say, well, if visible light communication was so good, why didn't we use our incandescent light bulbs, the old ones, right, to transmit data? Because we could also turn the light on and off. Well, those were too slow. Okay, so when you turn them on and off, the modulation is too slow, so you cannot transmit a lot of data. So what happened is that the blue LED was invented. And that was a great invention. It was worth a Nobel Prize for 3 people that invented that, right, in Japan. And sometimes you invent something and there's a trade-off. So you get A, but you lose B. But the LED was amazing. You got A, B, C, D. You got light that it was more efficient than the incandescent light bulb. It lasted longer, a longer lifetime. And not only that, because it's a diode, we could start modulating it at very fast speeds. And that's what allowed visible light communication to have a comeback. Because we have LEDs on your screens, on your cars. The lights that you have in street lights, every light that the human is generating now is an LED. So any light that you see could be transformed into a wireless transmitter. Now, before we continue, some pros and some cons of visible light communication. So visible light communication is not here to replace radio. Radio, I think, is going to be the ruling, it's not I think, it will be the ruling way of communication that we will have. It's just that visible light has some advantages, like giving us a little bit more bandwidth. One disadvantage of light is that it doesn't go through wall, but you could also see it as an advantage because it can remain safe inside the room. In fact, one of the companies that sells these products had a few years ago an agreement with the United States Army to use visible light communication for their system, so then it could not go through walls, and then you could not sniff that. Some people are having some arguments about how healthy radio frequency waves are. I don't think there's nothing certain there, but we know that light doesn't cause much problem. The disadvantages of visible light communication are coverage, as we said. Sometimes you move out of the light, and then you will not be well covered. Eye safety, and this is going to be important for modulating information, and user adoption. So people are just not going to be very happy changing the way they communicate from radio to light. A few examples, in case some of you are interested. I have met a few bachelor students and master students, and if you're interested in doing some projects, this is one project that we did. The European Union has fair in Brussels where they want to teach advanced concepts to children and teenagers. And we noticed that during COVID times in the UK, I'm not sure if that happened in Estonia, but in the UK, some people were burning 4G, 5G towers because there was a conspiracy theory that that was helping the dissemination of COVID germs. So we said it would be important if people will know that that's not the case. So how can we teach wireless communication to children? Now, if you transmit data, this phone, when I transmit data, will be like light. It will be like light going on. But it's so messy that it will be like being in a nightclub, in a bar, because the light will be oscillating. So it's very hard to teach people something that they cannot see. So we created these transmitters, and we started to teach wireless communication to kids with light, because it's the basic idea, and they could play with it. Another thing that we can do, and this is something that you will also learn, is that you could have any type of light also transmitting information, or any type of optical surface. What you will see on the top is just a normal window. I believe that this video is in Rotterdam Airport. You see the runway behind that glass panel, and it's just displaying information. But what we said is, and this is something that is being investigated in the research community, in the same way that you have an LED transmitting information, can we have screens transmitting information? And you can do that. So this was done, the prior project was done by 2 bachelor students on the robot, a little robot moving with light, and this was done by a master student. We took one screen, the same screen that you have in any device. You take the backlight from the back, which consumes more than 80% of the energy, and you just disassemble that, and you put it behind your window, and then sunlight will give you that information. And then you cut a lot of the costs. Of course, that will not work at night or when it's too cloudy. But here what you see is just that screen behind this normal window, and sunlight is giving the information. Now, what we did with this company that sells these panels, we said, well, what happens if you're in the airport and one part of the screen is showing news, the other one cartoons or videos, depending if you're an adult, a kid, or a teenager? What if we start transmitting more information? What you will see now is that in this image, there's a video. This student likes Coldplay, gets the phone, so then light is coming, we are modulating that information, you see the video, but then you can also get some information to start getting other type of data. And the other video is exactly the same, it's just that we do it in color. One is in black and white, the other one in color. Good. So what is what you're going to be learning during these 3 hours, 1.5 hours today, then on Wednesday? The physical layer. How do we transmit that data, and how could you use those methods to create your own link if you want? There's going to be perhaps some information about the hardware, just what you need to keep in mind if you want to develop these systems. We are not going to be covering the data link layer, while the network layer is just the IP addresses and above. And there's some information on data link layers, but we are not going to be covering that. So this lecture is going to be LED to photodiode. And the next lecture is going to see how we can use a screen, cameras, and even sunlight to transmit this information, and also some topics on sensing. Good, that was part 1. And what is the message? What we want to learn is let's just put here. So the first thing was part 1. And then we said that light was there. Then came radio. But bandwidth became expensive. And after that, the LED came, and we have visible light communication making a comeback. So that's the reason why we are having some work now on visible light communication. The next part, it's on modulation. How do we convey that information? And this is the part where there's going to be a small exam, because this is where I'm the most interested that you learn something. Okay, the basics. So if you have a budget of roughly, let's say 30 euros, 40 euros, what you do is you get a couple of small Arduinos, Nano. You just buy an LED, a resistor, you connect it on one Arduino, and then on the other side you have a photodiode. This is just an op-amp. You do not need to know what that is. It just converts current into voltage. So we are transmitting data from this device to this other device. Very inexpensive, okay? And that will give you the basics. You will not be able to transmit video with this. For video, you will need to have a BBB, a big old black bone device. But this is going just to be the basics if you want to develop a link. This will allow you to do quite a few things, as we will see, though, in the next lecture, even this basic set. Okay, so there are two key challenges when you have light. Because you could argue, well, we have been modulating radio for so long, so what's the big deal about light? What do we need to consider? One thing is flickering. So you see that there, and I'm going to stop it because if I continue, you're going to have a headache. Radio waves cannot be seen by humans. So there's more freedom on how much power we are going to put when we want the antenna of your devices to transmit data. There's kind of beams of lights radiating out of here. It's just that we cannot see them. But we can see light. And the most important thing of light is illumination. So whatever we do, we cannot create flickering effects, period. That's your number one constraint. There's another point, which is dimming. It's not the same as flickering. This is when, let me stop it too. This is when you have these lights now that you can control the amount of illumination. If you have some light coming from outside, you do not need that to be so intense. Or even if you're in a bar or in different places, you just want to control the amount of dimming that you have there. Good. Now, this is what I will do. When I teach at TU Delft, for the first time, I do the following. I give my students questions. I'm not expecting them to know. So then I give them the questions, I see the answers, then I teach the method, and then I ask those questions again to see if they learn what I was teaching. So that's what we are going to do now. You do not need to know. I'm expecting maybe here that the answers will be, random. But let's just see. And then I will ask these questions again. So let me close. Boom. So what type of modulation provides the higher data rate? So for now, don't focus about flickering or dimming. We just want to send as much data as possible. So which one of these do you think would be good? Huh? And if you don't know anything, just choose randomly one of them. Okay, so the results. Variable pulse modulation. I will not say if it's right or wrong. I will leave it up there. And then hopefully, if I teach things right, you will get the right answer, which may be that one or a different one. But let's just write it down, because I will. So for the first question, Q1, most of you said variable pulse modulation. Okay.
Is Manchester a thing?
Sorry?
Is Manchester a thing?
It's good. It's an encoding that you use on top of modulation. Manchester encoding is called. Good. Now, okay, let's just see the next one. Now, which one of these modulation methods have lower flickering effects? So now I am not interested on sending as much data as possible. I want to give you a light, and I don't want to cause that much flicker. Okay, I don't want this to be causing that flicker. Okay, so let me see. I will start showing the results. Okay, so now we have, for Q2, we have almost, let's say 45%. Things is okay. Okay, last question. Which one of these modulation methods is better to avoid flickering and to have dimming as well? Once again, flickering is we don't want this light to be annoying, but we also want to have the ability to just change the amount of illumination if, don't check ChatGPT or anything, huh? Don't follow Jack's advice, just try to do your best guess. Okay, we are almost there, so I think I will not bias the results if I show them now. And now there's a tie between Manchester and BPM, it's almost tied, so let's just say Q3, Manchester and BPM. Okay. Good, let's stop this. So there are good news and bad news. The good news is that you got it wrong. So then The bad news is that then you cannot sleep over the next roughly 20 or 30 minutes if you want to learn and get the right answer. So I'm going to ask exactly these same questions by the time that I teach. And I would say that it's very hard to pay attention during a lecture. It happens to me too. But I always tell my students, when I see they are sleeping, I said, just right now, be awake, because this is important. So I will tell you, if you slept before, that's okay. If you're going to sleep during the next lecture, it's okay too, I guess. But don't sleep now, because this is where you will teach the basics of just transmitting all this data. Okay, good. So, first of all, there are multiple modulation methods. There are multiple ways in which we can control that light to send information. The one that you saw on the video, the TED talk that I showed at the beginning, is continuous time. So it's the one, there. It uses something called OFDM, orthogonal frequency multiplexing, and it's a complex method, but it allows you to send a lot of data. So we are not going to teach that. That requires quite a bit of mathematics for the understanding. Well, there's also color domain. You can use different colors, frequency domain. We are going to use the one that are called pulse-based modulation. This is going to be the focus of this lecture. Now, the good news is that even with these techniques that you are going to see, they are very easy. You will be able to transmit, if you want, video with a light that is not flickering, if you have a BeagleBone black. Okay? So that's going to be the focus of this lecture. Now, let's start with some definitions. Do not worry much about it. First, you see something called the time slot. So let's say that you have a light, and you start turning that light on and off. At the beginning, you can do this, let's say, for 5 seconds, 10 seconds, 1 minute. And then you can start reducing this time, and you can keep on reducing. But you cannot make this reduction infinitesimally small. At one point, you can no longer reduce this, and we will look into why that is. So for now, assume that the time slot, the T slot that you see there, is just the fastest that we can shorten this period. Okay, so that's T slot. Now, symbols are going to be if the light is on and off, and the amount of bits that we can transmit, it can change. So sometimes one symbol can send 1 bit, but sometimes one symbol can send multiple bits, or sometimes we need multiple symbols to transmit 1 bit. I know that could be confusing. You can forget about it. The only important point is that we have the light turning on and off, and I will tell you how to transmit bits without causing flickering and by allowing dimming. That's the important thing. And at the end, we have just the equation of throughput. You will have these slides later. I think it's more important that you understand the concept, because the math, you can always check it. Okay, so the basics. On-off keying, which is the first technique that we show in those questions, is just mapping when the light is on to 1 and when the light is off to 0. So you just get any data, video, text, you convert it to a bunch of 1s and 0s, and then you just have your microcontroller sending those pulses. Okay? And then we send that information. Now, what is the problem with that? The problem with that is that it could cause flickering. So you could say, why don't we send it faster and faster and faster? Well, there's a problem. At one point, I will tell you what the problem is. So let's say that if you send a series of 1s and 0s, and you make it faster, then you do not cause flickering, because your eye, what it does is it sort of averages the intensity. But what if, instead of sending this, I send 0, 0, 0, 0, 1, 1, 1, 1, 1, because it could happen. Now you're going to have long periods of 0s and long periods of 1s, and that will cause flicker, because it's going to be equivalent to just having longer 0s or longer 1s. We don't want that. And so you do Manchester encoding, you will have a high data rate, because every symbol transmits 1 bit, so that's the highest amount of information that you can transfer. That's good, but it will cause this annoying flickering effect. So what is what you do? If you want to avoid flicker, you do something called Manchester encoding. What is the key idea? We want to make sure that over any period of time t that we have, the average intensity, let's say, remains at 50%. So there are the same number of ones and the same number of zeros, because in that way I can guarantee that my average intensity is going to be the same. So what you do is, and this is what you're observing here, instead of having 0 is this and 1 is that, I'm not sure if you can, I think you can see it. What we are going to have is that now 0, for example, let's say here, is going to be 1 high and 1 low, and 1 is going to be 1 low and 1 high. Now, it doesn't matter what pattern you are sending, always your average will be at 50%. What is the problem with this? Anybody wants to say what the problem with this is? Yes? Half the data rate. So now, here, with 2 symbols, we transmitted 2 bits. So this is 2 symbols. Let me just use so we had, oh yes, there will be, so 2 symbols transmit 2 bits, and here we have 1, 2, 3, 4 symbols that are transmitting 2 bits. So we need more time to transmit the data. Yes, there's a question.
Okay, so my question is, when you start reading the light, like ons and offs from the wrong place, even if you shift it like one place to the left, then you get the bits inverted.
Ah, okay, I understand what you mean. So, so the question is this. So if I send you, good question. If this is a 0 and this is a 1, let's say that I get the wrong place, I start measuring the data here. This is going to be read as a 0, and this will carry on and give me a bunch of bit errors, which is not what I wanted. Okay, good. So that's a good question. What happens when you develop a system, what I am not mentioning here is that when you send a packet, there's something called a header. So you just don't transmit the data like that. First, if you have data, then you put this data into a bunch of ones and zeros, video, images, whatever you want. And that's going to be on the okay, I don't think you can see this. This is going to be called payload. Payload. But before the payload, you have something like a header. And what this header will give you is some level of synchronization, so you never have the problem that you are talking about. So if you want to do this, this is a good point, because I'm just teaching you how to transmit data like crazy. No, that's not what you're going to do. What I suggest is just go to your Arduino, you type your name, you convert that to ones and zeros, but before that, you're going to send a preamble, a specific type of sequence that the receiver will say, oh, I know the data is starting exactly at this point, so you can always decode it right. Okay? Good question. Any other questions until now? Well, this just, sorry, I cannot hear.
If you can like randomize the payload.
If I sort what?
Randomize it.
If I randomize the payload?
Yeah, randomize it, and then in the header there, information metadata, you have a seed where it will be de-randomized at the reception.
Yeah, you will not randomize the payload just for the sake of challenging yourself, but what you could do, and that's what happens when you do encryption, right? So but then you have to have a key. So
it's like a just simple randomization so that you can get like even number of zeros and ones.
Yes, there are different ways, mechanisms in which you try to make sure that you don't get out of sync with your data. Mm-hmm. But the one that it would be the simplest that I would suggest that you do, you just get your Arduino, put your name, zeros and ones, put a simple sequence here. 4 or 5 symbols that are very unique, and then after that you start detecting them. Good questions, especially because you do not have a background in communications or electrical engineering. There's a page called OpenVLC. This is one of my colleagues. And you can download the code. So if you have a BeagleBone Black, what you will be able to do is, just with Manchester encoding, they will be able to, you can send...
over created with light. and as it can be seen, it is able to transmit video at a maximum created with light. And as it can be seen, it is able to transmit video at a maximum.
Video that you see there, and I think they're transmitting at 400 kbps, so standard video definition requires 500 kbps or so. Big old bone black with a good header. There's something else called error correction and error detection, because your bits may fail, and that's something that you need to add to prevent for that. But the basics, just the basics, sending the data with Manchester encoding will allow you to send even a video, something as simple as that. Good, so we said that OK, let me stop the flickering. OK was providing the highest data rate because one symbol maps to one bit. But that causes flickering, and now we have Manchester encoding, which guarantees that the average illumination is going to be 50% no matter what, and that solves the flickering problem. So now let's look at dimming. Once again, dimming is just, I feel like I want to relax, I want to turn down my light a little bit, or I feel happy, and I'm going to turn it on. So what's the problem? The problem with OK Manchester coding is that the light always remains at 50%. So somebody says, well, I don't want to have this maximum light, I want something lower. Well, sorry, I cannot do it. You want something higher? Well, I cannot do it either. It remains at 50% because every bit just has two symbols. One of the other problems, as you mentioned, is that the throughput is divided by 2. So keep that in mind, right? We do not support dimming. So how can you support dimming and also do not cause flickering? And that's variable pulse position modulation. So what you do is the following. It's once again a simple concept. We have said the Manchester encoding is 0, 1, and 1, 0. And then what you could do is you could take even more time slots. And now if you have 4 time slots and only 1 slot is on, you have a dimming of 25%. Right, so you can start, and if you want to have to 80%, then you have 4 slots on and 1 off. And in that simple way, you can get both almost 0 flickering or very little, and you can control the dimming. But what is what you are losing? Sorry, somebody said the right answer. Throughput? Throughput, exactly, because now, here there was 2 symbols gave me 2 bits. Here, 4 symbols gives me 2 bits. Sometimes now it's going to be 10 symbols that are required to transmit 2 bits. So there's no free lunch. You will always need to pay something for what you are doing. We support dimming. Throughput drops quickly. What happens? This is the LED brightness. Throughput, the amount of data that we transmit is there. We have OK and Manchester coding. Notice that it's in the middle. It's in the middle because it's not fully on, not 100%, not off, 0%. It's just in the middle at 50%. And then this position modulation that we have, it just starts decreasing the data rate when we move out of there. That's the S that you observe there. Is there a better idea to increase the data rate? Yes, but this is the last part of the modulation. Oh, question? Yes, sorry, go ahead. Can somebody pass the mic, please?
Thanks. Why would you need to, I wonder, keep it at 2 symbols for 1 bit and not have the light dimmed, but still read that it's a 0 and a 1,
Oh, you could do that. And for most lights, that would be okay. Mm-hmm. So if you do not need to dim your light, you stop there, because then that would be good for you. It's only if you have the requirement to dim your light, because the user wants that for some reason, that then you need something extra.
No, I understand that. My point is that, let's say you have your light at 50% dimmed because you are using Manchester encoding, but then you reduce it to 25%, and still there is light in which you can distinguish zeros and ones.
Oh, I see what you're saying. I understand. So you could dim light in 2 ways, in the analog domain and in the digital domain. So short answer for you, let me explain the question so for everybody else. So I think what he's saying is the following. We have 2 options to obtain 25%. One of them is to use more symbols, but that reduces the throughput. Or the other one is that we modify the hardware, so then actually the intensity decreases, but we can still transmit the same amount of data. Short answer to your question is yes. The only thing that may cause is increased costs on the hardware that you are going to use, and sometimes digital modulation is the easier way to do things. And that's what most modern lights do, because it's a cheaper mechanism. But what you're saying is right. Okay, so the last thing that we can do is if we have 5 time slots, and we have an intensity of, in this case, 80%, because 4 lights are on, we can change the location of where that light is turning on. It could be the first one, it could be the second one, third, fourth, or fifth, and now we can transmit more bits with those 5 symbols, because the first combination could represent a 1, 1, the next one 0, 1, so on and so forth. So in that way, we can increase just a little bit the amount of data that we are transmitting. Okay, we do not need to go into the math. There's some stuff there. And now, let's see if we can answer the questions. There are different methods that this is the last modulation method that I explained, where you have 5 symbols, and you can transmit up to 2 symbols, 2 bits per symbol. That's the MPPM that you see there. Now, let's go back to the questions. I think you got them, almost all of them, wrong at the beginning. I forgot where I wrote the answers. Oh, no, they're there, but I didn't put the percentages. Okay, so now let me just, yeah, let's see if it works. So which one of these methods provides the highest data rate? So there's 39 out of 39. Now these were the old results. Now I see more coming. Okay, so then I can see that now you are going for OK. That's good. I think you got the message. Some of you are saying Manchester, the highest data rate. Okay. Okay. Now let's go with the next one. I think that you got the idea of OK. Now, which one of them provides the lower flickering effects? Let's just build on top of what we had before. OK. So the right answer for the prior one was OK. The right answer for this one is Manchester. Good. And now the last one. So which one of these provides lower flickering effects and better dimming properties? Let me see, I'm just going to open it now. And you have variable pulse modulation. So that's good, because at the beginning, as you saw, the answers were all over the place, and I think most of you got the basic ideas about how you can modulate. Thanks. Let me just go back. Any questions up to this point? Because this is going to be just the core of the modulation part, how you control those 1s and 0s to transmit data. Any questions? Yes, one.
I have a general question. It's not about this topic per se. It's about the beginning of your talk. You said that big companies, they pay a lot of money to buy bandwidth spectra, and visual light communication is free. But will it stay free if we start using it on scale?
So the question is, right now the visible light spectrum is free. But if we start using it at larger scales, with the governments now start charging us for using the visible light spectrum? That's a good question. So far, no. The standard said that it's free. So otherwise, it would be a little bit tricky, since if I turn on my light, I'm using the spectrum. I'm not transmitting data, but I'm using it. So it starts getting kind of tricky to go there. So far, it's not. Maybe later they will do it. But that's an advantage. Good point. Any other questions? Because this is now almost where we are going to stop with modulations. I have a question for you. What happens when the lights are off? We don't transmit data. Can we transmit data? And this is some work that tried to look into it. This is a 1-minute video. It will capture the basic idea, because now you know pulse-based modulation. You will see what option is there.
Visible light communication is emerging with promising capabilities. It offers secure, wide bandwidth by reusing light. Visible light communication is emerging with promising capabilities. What do we do when the lights go out? It offers secure, wide bandwidth by reusing light. A new light communication keep our lights on. Operates even when the lights appear on. What do we do when the lights go out? It encodes data producing dark light pulses. A new light imperceptible to human that operates even when the lights appear off. The transmitter is an off-the-shelf ultra-short light connected to an FPGA generating short light pulses not photodiode data. The transmitter is an off-the-shelf photodiode connected to an FPGA generating short light pulses to transmit the LED scenes off. The receiver uses a low-cost photodiode to allow customized circuit. Dark light uses 100,000 times less power than normal light communication. Data is transmitted a distance of up to 1.8 meters. Dark light uses 100,000 times less power than normal light communication by reusing and supports a distance of up to 1.8 meters. It also broadens the applications by allowing visible light communication and easily accessible by reusing light around us. Dark it also broadens low-cost alternatives by allowing visible light communication and sensing regardless of light status.
Okay, so just to make sure if
it's a low-cost alternative,
it was clear, now you know that you know pulse-based modulation, just playing with the pulses to transmit light. Can anybody give me the basic idea of that video? How can you have a light off and still transmit data? Exactly, to turn it on, but for a short period of time, so it's not visible. So that's the trick that you play. But the price that you pay for doing that is that your data rate goes really, really low. Okay? But that's what you can do. Okay, so as I mentioned at the beginning of this second part, there are multiple modulation methods. If you really want to reach megabits per second, 30, 40 megabits per second, this OFDM part is what you should do, but it's more complex. And now in research, they are showing links of gigabits per second with LEDs. And there are other modulation methods, but we will not have time to cover those. So let's just do now again a small summary of where we are in the lectures. So the first message that I wanted to convey was why we are going with light and its bandwidth. We had the LED coming to the rescue. Part 2 is then how we modulate that LED, so modulation. And we mentioned that one of the key things is that because humans can see light, but they cannot see radio frequency, we need to be careful about how we do that. And we have checked these very basic methods. One of them was OK, very simple, high data rate. The data rate is high, but it can cause flicker. To overcome that, we can put Manchester encoding on top of it. Now, the data rate is going to be lower, but we avoid flicker. So no flicker. Or maybe let's put a check. So we can cope with that. Neither of these two methods will support dimming. Actually, OK can support dimming perhaps to some extent, but then we have this variable pulse modulation where the data rate keeps on going lower, but we can control flickering, and we can also do some dimming. Okay? So those are the two messages that we have conveyed so far in the lecture. Now, the next part, any questions? By the way, I also have time if there are more questions, otherwise we could finish a little bit earlier because I'm going to enter now the part of hardware. This is something, there are tons of LEDs, tons of photodiodes, and then you could say, okay, Marco, I would like to develop this system. How do I choose them? And there's a few more things that you will need to learn. And that's what we are going to enter now. But if you have any questions about the motivation or modulation, this is a better time. Yes?
For the setups that you have here, I mean, does the environment has to be controlled, I mean, to eliminate any kind of noise? I mean, other source of noise or other source of light?
So the question is, when we use light, we need a controlled setup because, for example, if here we will open the windows and sunlight will come, that will be the equivalent of interference, and hence things may not work out that well. That's your question? Yeah. So, good question. And we are going to cover a little bit of that in the next part about how you select your hardware, which one is the best way to go. But to give you a short answer, just if you have other lights interfering, the performance will degrade, but it's not that it cannot work. There's going to be some reduction in performance, but you can still have a few methods that you can do to still transmit data. Okay. Good. Part 3, hardware. This is going to be a little bit, hopefully I will try not to make it too heavy, but I need to teach it so you understand now what you... Okay, this looks horrible, right? So I show you this slide and maybe half of you will go to sleep, but I will draw it because the drawing is always better to try to explain what happens. I just put it there so you have it in the slides. So this slide just tries to capture a short story about how your data gets completely distorted when it goes from that transmitter to that receiver and why that happens and why we need so much research and there has been so much effort into the area of wireless communication and embedded systems. This is what happens. So you have your data here. That would be the point DT there, okay? Data. And you have your perfect wave capturing your ones and zeros. That's Disneyland, that's the ideal world, and the ideal world stops there. Because once you have your transmitter, okay, I'm not sure if, let me put this in here. That signal that is going from DT to ST is going to have a distortion. By the way, when you review these slides and the lectures, that's what is being trying to capture on that last column. At the beginning, you see this perfect square wave. That would be this wave here. Now, this transmitter is not going to send a perfect wave. When you start using this transmitter, what is happening, and we're going to see why in a minute, the square wave is going to start looking at something like this. Now, you increase the speed, this signal is going to start looking at something like that. You want to increase the speed more, this is going to look something like that. You want to increase the speed more, now this is going to look like that. You increase the speed more, and this is going to be a flat line. And that's the bandwidth of your transmitter. Your transmitter just cannot increase the speed to any speed that you want. It will have a limit. Okay, the LED, we will see, has a limit. So your initial beautiful wave is going to start getting distorted. Okay, so that's the first distortion, the one that you see the second row there. Then this is going to travel through the channel. So we are going to be having the channel, and there's going to be now noise. First of all, this signal is going to get tinier because it's propagating. So this big signal, now for now, let me erase this, is going to start getting smaller and smaller. And you're also going to have noise. Finally, you're going to have your receiver, your photodiode, and your receiver, like your transmitter, is going to have some bandwidth, and it's going to say, you're sending me this data, I don't care, I'm going to distort it even more. So this beautiful signal that you have at the beginning, these square waves, they do not exist in reality, and they're going to have a lot of these transformations. Now, what I'm going to show next is how you can choose your components to try to have a system that is relatively fast, and still you try to overcome some of these problems. Okay? Because now you know the modulation methods, but if we stop there, which one of the, I don't know, hundreds of thousands of LEDs are you going to choose and why? And which photodiode are you going to choose and why? And that's an important part. That's what we are going to cover now. Okay, so first, just so we appreciate what has been done over decades. The image that you see there on the airplane is memory in the 1950s, 5 megabytes, not much. 1 ton. And what you see there later is something that is already like 10, 12 years old. It has 1 million more memory, and it's just that small. And all that is because it's a diode. And a diode is just these super tiny things, right? These materials that are at the core of what we do now in computing. And your receptor is a photodiode, so it's a diode after all. And your light is a light-emitting diode. So it gives you all these nice properties in terms of speed. Okay, transmitter, LEDs. What properties are relevant when we want to use these LEDs not only for illumination but for visible light communication? What happens with your LED is the following. So I'm going to try to explain now on the board that image that is there. What is the important thing in that image is that you see that the electrical current, so we turn on our LED, but our LED is not turning at the right time. There's some delay. And then it turns on, and then by the time that we turn it off, there's going to be some time. Similar when you try to control water in your shower. You put warm, does it get instantly? No, it takes some time. You want it cold? No. So these are just playing around. Similar principle there, but it's because there's a capacitance effect. Okay? You do not need to know anything about the capacitors, but that's one of the problems. Now, what that causes is, look at the shape. Here on the x-axis, we start increasing the voltage. And on the y-axis, we have the optical power. It is not something like the square waves that we have been seeing so far. It is something more like this. Right? So what I've been telling you that you just turn your light on and off, it's kind of a white lie. It will work. Your system will work. But if you really want to develop a system that is more efficient, you just do not turn your light on and off completely. What you do is you keep it in the middle point. Do you see that middle point there? That's kind of having your LED in this middle of the road state. So then you can just move it around the linear component. So in that way, what you will create is, instead of having a signal that looks like this, you will have more a signal that looks like a trapezoid. Not ideal still, but just not so distorted. That's very hard to do. So if you would like to do your visible light communication link, do not do this yet, because this will require quite a lot of knowledge on electronics. You can just turn your light on and off completely, which is very easy to do with your microcontroller and code, but just be aware that this is the distortion that will be caused. Okay, so that's point one. This is just to show you how you really modulate light in a real, more commercial method, and not just for the purposes of doing a basic prototype. When you buy your LED, there's going to be a lot of information. The important one that you need to check is just the bandwidth, the time response. This is the part that you see there. The time response just says how much time it takes to go up or to go low. The fastest the time response, the more data that you will be able to send. So you get your LED, look at the data sheet, check time response. If it's very short, this is going to be a good LED for you. That part that you see on the right, it captures it. It just says, maybe I can connect this plot that you see there with what we discussed before. Look what happens at the frequency between, in the x-axis, between 0 and 10 megahertz. Look at the amplitude, the relative amplitude. It's a flat line. That means that at the beginning, when you start increasing the modulation, this amplitude A remains the same, remains the same, remains the same up to a certain speed. After that, if you keep on increasing the speed, that amplitude is going to start reducing. Okay? So you just look at that plot. Receiver and photodiodes. Let me just, okay. This is going to be one of the questions that I have. Let me see, where is that question? Maybe, just to bring you back, because I don't want you to fall asleep, let me ask this question now. Question 8. Tab. I don't have the images here, but there's going to be this question. Just do not answer yet, do not answer yet, do not answer, because I want to show you what the question is about. Imagine that you have one transmitter, which is that LED, and that spectrum shows, for example, that I'm sending information between red and blue. That's the spectrum, okay? We are in a dark room. This is related to the question that was asked before. We are in a dark room. So we are transmitting information with that LED, and we have our receiver, and we have two types of receivers. One receiver that has a narrow spectrum, so I cannot cover everything that is being transmitted, and one receiver that is wide, so I can get all the spectrum that the light is transmitting, but also more noise. The question that I have is, considering these two systems, which photodiode would you use if the room is dark? Does the question make sense? Yeah? So then you can go and answer. So which one of these two you would choose? Once again, we are in a dark room. I will let you look at this image, and then I will just show the results. Let me see now, because I don't. You say narrow, most of you, oh, okay. Okay, let's see just the next question. So we have between narrow and wide, it's relatively close, 60 and 40%. Now, look at this question. Now there's light, there's noise. So for the question that was asked before, I have the same transmitter, the same LED, but now I open the windows, so I will have sunlight interference. So the question is, which one is better to use, the photodiode with that narrow spectrum or the photodiode with the wider spectrum? So for the first one, most of you mentioned, well, it was 60-40. So Q8, it was 60 wide, 40 narrow, roughly. And now let's see what you get for this one. Show the results. Okay, I think your intuition is pretty good for both of them. For the first one, the answer was the wide one, and for this one is the narrow one. So let me ask why. So I want to hear an answer first for the first question. So for this one, why is it better to use a wide one? For those of you that answer wide. Right, so the answer was, and is the right answer, since we do not have interference, our LED is transmitting the data, and if we have a white one, we get all this data, that's the signal S, which is good, and there's no noise here. There's no noise because there's no light interfering. And for the next one, what happens is that it's better to have something narrow. Let me just get a look at it. It's better to have something narrow, because if we have something wide, all this noise is going to start accumulating. So this is a little bit of the answer for the question that was asked about interference. So it's important that you try to look for a photodiode whose spectrum is relatively similar to the light that you are transmitting. If you are transmitting with visible light and you use a photodiode that has the infrared spectrum, that's not going to be good. So try to check in the data sheet that both of them coincide. And finally, you also need a photodiode that is a little bit fast. This rise and fall time, it just tells you how fast or slow the photodiode will be. Let me do one thing now. Let me show you an application before I show the next part. This is something that was done by a master's student in my team. I have explained you now the transmitter. You need to check just how fast you can send information. And for that receiver, you also need to see if you can receive that information fast. But you also need to see that the spectrum matches the transmitter, depending on your situation. Here what we do is, you see this light is going to be sending information, and on the top you will have a receiver with an IMU sensor, just accelerometer, gyroscope. And look what happens. We start moving the receiver, and we start getting the localization of the system. I have a question for you. Is there something just puzzling that you find in this localization system? We have one light that is transmitting data, and we have the receiver, which just has a photodiode and an IMU sensor. But we have one transmitter and one receiver. Anything that you will question on this localization system? That just doesn't sound right. Hint, think about GPS. Sorry?
Typically you need 3.
Yes. The answer was typically you need 3. So if you have your GPS satellites, if I just give you one transmitter, you don't know where you are. You know you are in that circle, but you have no idea where you are exactly. I need to tell you 2 and a third one to give you a localization in 2D, in 2 dimensions, and I need 4 to give you the localization in 3 dimensions. So now I'm localizing in 2D, but still I only have one transmitter. And so how could you do that? And the reason is, and over the next part, I will not start giving all the math because that's not the important thing, but I will just give you a basic idea. What happens is the following. Light has something called, not light on its own, because the sun radiates energy almost like a point source in all directions. But if you see light, it has sort of a Lambertian pattern, right? Actually, let me turn on my flashlight here. I'm not sure if you will see it. Yeah, maybe. You see, it has sort of this Lambertian pattern, which is different just from what a radio tries to do of sending in all directions. So what is the trick that you play there? If I show you my phone like this and you see my flashlight, you're going to be receiving some information. But if I turn it around, the light intensity that you receive is going to be different. You can be exactly in the same position. Notice that I'm not changing the X, Y, Z coordinates. I'm just rotating the device. So in this case, once you have the transmitter and the receiver at 2 locations, you only get one isocontour, the red one there. So you do not know where you are, but you know that you are somewhere there. Once you move just a little bit, you create a second isocontour, the blue one that you see there. And by having the intersection of those 2, that's how we can get localization. And that's the reason why you see the movement here. We start moving, and we are internally calculating the different isocontours and just obtaining the localization. Because we have 10 minutes and because it's late and I don't want to bore you down with the details, if you want to achieve that, once again, I have a question actually. How much time do you have for the master thesis at Tartu? How long is
Typically they do from October, November to mid-May.
Okay, so then you have 7 months, good 6, 7 months, 8 months, 6, 7. So some of the projects that I have shown were done by master students. At TEL Delft is a little bit longer than that, but something similar. So many of these topics could be covered if you want, and there's a lot of this work done by computer scientists, because a lot of the hardware part, you can just use off-the-shelf components. Now, this is the last part. And if you want to understand just a tiny bit of the math that was behind that paper, I will try to explain it in a very simple manner. So this is just the last point of attention, and we are done with this lecture. That Lambertian pattern that you saw, that I put there when I put my flashlight, is this equation that you see here. And it looks, kind of boring, intimidating, but I will try to decompose it for you so you could understand what's going on. Let me just first give this example. We have explained about the transmitter. It needs to be fast. We have talked about the receiver. The spectrums need to be similar, and it also needs to be fast, but we have not talked about the channel. Now we are talking about the channel. Okay, this is the middle point of the LED. Transmitter, receiver, channel, and that equation that you see there, we are going to decompose it in these three parts. You turn on your light. That's the PT that you see here, is this output power. Okay, that's just the energy that you have on your light. More energy, more light, and vice versa. That's the PT. So you turn on your light. After that, you will see this component M. And that component M is called the radiation pattern of the LED. Okay. And you can have an LED that is long and wide, and this is going to be a big M. Or you can have an LED that is sort of shorter and wider, and that's going to be a smaller M. This is just the pattern of the LED. Okay, so that's the second component, M plus 1 over 2 pi. Then you see this cosine. And what that says is that when light is, so that's the pattern M. So we have power PT, pattern M, and then we have this cosine. That cosine is saying the following. When you're on your LED and you're looking at it directly, you're going to have the highest intensity, right? So at that angle, you're getting the highest. Now, if you start moving out of this, you're going to receive a lower intensity. So that's just the cosine angle with respect to this point. So you start moving, and your light intensity starts reducing. After that, you go through the channel, and this is just a decrease into 1 over d squared. So as your light starts traveling, the intensity starts decreasing. So this is the transmitter, this is the receiver, and finally, when you get to the receiver, there are some important things that matter. One is also the angle, how relative you are, this angle theta. It also matters the area of your receiver. The more area that you have, the more light that you're going to receive, but also the more noise and the slower your receiver is going to be. That's the area. And finally, you have your received power. Okay, that last received power and this equation is what allows us to build this system that I just mentioned there. With that, I think it's time. Let me just wrap up the third part, and that's going to be the end of the lecture. And I promise that the next lecture has no equations. So it's just about systems that you can just go. But I needed you to understand a little bit of the math behind it. So the recap of this lecture has been why we need light, because bandwidth is getting expensive, and LEDs came. If you want to develop your visible light communication system between a light, an LED, and a photodiode, there are two main components: the modulation scheme that you're going to use and the hardware that you need to choose. Part 2 was the modulation scheme, focusing on avoiding flicker and trying to give you dimming options. And part 3 was about that hardware and understanding that channel. So it's not, with any LED and any photodiode, you will create a link. But if you want to create a fast, high-performing link, then you need to make sure that your LED has a high bandwidth, so you do not see those distortions. And you need to make sure that your receiver also has a high bandwidth and that the spectrum are relatively similar, so you can capture all that information. Now, in the middle of the transmitter and receiver, there's some mathematics embedded in how light is disseminated when we put an enclosure on the LED. And that's the Lambertian pattern. And if you understand that math, then you will be able to do more things, not only on communication, but things like sensing and localization. With that, we conclude this part of the lecture, and I will tell you how this is used for drones. There was somebody doing research in drones. This is a project that I started recently. We are not going to ask those questions again. I already showed you this video, right, of the localization, but we did the following. We said, in the old times, ships in the ocean needed house lights to give some idea on navigation. Otherwise, they will crash. That's the way that we help them. So now one of the things that we are doing is we are saying, Nowadays, we have so many LEDs inside, so these LEDs could be the modern lighthouses to transmit data. So these LEDs, if I have a drone, could tell the drone, right now you're in the delta in this room, send information, communicate to the drone, provide localization at the same time, and then you can start moving around. And this is something that now we are doing. And in this case, what you're going to see is these 4 lights are just transmitting information. This little drone is moving. This pole that you see here is just for the ground truth, but then we can transmit data, tell the drone to move, and then at the same time start providing localization. And localization with light usually is more accurate than with radio frequency because radio frequency is very noisy. So the key message that I want to convey to you is that these techniques that I've been mentioning is not only to transform every LED into a transmitter for a photodiode, but it could be included in many areas of computer science, pervasive computing, ubiquitous computing, human-computer interaction, and we will see a few more later. Okay? With those ones, I will not ask these questions again, and then on Wednesday we are going to continue with part 4. Any questions? Any final questions? There's a question there. Yes, I can hear, and I can repeat your question so it can be heard in the recording.
All right, so I just wanted to know, I was intrigued to know in one of the slides that you mentioned, the motivation part. So I was thinking, is there a context of visible light communication that can be used in the healthcare? For example, variables, healthcare variables, where we can have like biosensors or smart guard or something that we can use visible light communication for. Or something like a line of sight could be an issue while implementing that.
Sorry, to understand your question, you mean, for instance, for healthcare, you mean like to localize medical equipment or to measure the organs of people?
No, I mean like they can be, for example, right now we have battery-powered devices, so we could use visible light communication for that, especially in outdoor settings.
Multi-power devices?
No, right now we have battery-powered devices. So is there a situation where you can see that visible light communication can be used to power those devices, medical devices, health variables?
Yeah, I think I understand your question now.
Yeah.
So now we have battery-powered devices, but visible light communication, if it could also be used to power the devices themselves.
Yeah.
We are going to talk a little bit of that in the next lecture.
Okay.
There's a method called passive communication with light. And what they do is the following. They have not even a battery, just a super cap to be eco-friendly because batteries. They put a solar panel, so then the light gives power. And then what you do is you just reflect light to transmit information. So with very little power, by very little power I mean microwatts, then you can get light. So it sends information but also energy. So I charge my super cap and I can reply back without an LED, just by reflecting information. So short answer is yes, that could be possible. Actually, in one of the projects that we had with one master student, we had a drone and we wanted to monitor something on the ground, soil, let's say humidity, temperature. And instead of transmitting data with radio, the drone had a light. So it got close to the sensor, the light charged the sensor, and then we receive information just by backscattering that light. So things like that are possible.
Okay.
Mm-hmm.
Okay.
Yes, question here.
About the drone application, how much is that like robust? Because we also have a light, and everyone, I wonder that everyone can intervene that kind of communication or localization. So how much is that robust?
Good question. So I have a drone, and let's say that our little drone is flying, and I want to be naughty, and I put my light, and my drone just falls down. Something like that, right? So that's your question.
Yes.
Good question. So let me just turn on this flashlight. If the light is constant, meaning that it's DC, there are ways in which we can filter that information. Okay? So that's not so hard to do because we can get it out. If you start modulating that light, then there could be a little bit more of a problem, and you will need to use more advanced encoding techniques in the same way that for cellular systems we have things like CDMA, code division multiple access, to have multiple transmissions at the same time. But I am not so aware with that part of research.
Thank you.
Welcome. Actually, a nice comment related to this, when we taught the kids. So when we went to the EU, we brought a flashlight. Okay? Oh, there's a question there. While the question is getting there, I will tell you the story. So we gave them a flashlight, and we told the kids, look, with this normal flashlight,
yes. Yes, thank you for your nice presentation. I have one question. Because it seems, if I understand correctly, it seems you use one or few LEDs for the communication, right? But what about in this room? We have so many LEDs. So maybe other LEDs can also be used for communication, and these LEDs maybe can be also the interference for your communication, not the outside environment like sunlight can be the interference, but the inside other LEDs, if we don't use it for communication, maybe they can also be the interference for your systems. So maybe you can have to clarify if this kind of issue can be solved or not, like in this room.
You're right. The question, if I understand correctly, is the following. So let's say I am under this light.
Yes.
I'm going to be receiving information, but now there's also that light.
Yes.
And so the two cones of illumination will have a point that I overlap somewhere around here, and I will be interfered by those two lights.
Yes.
That's your question. So that's solved by in the data link layer, medium access control, when you have multiple systems that need to communicate with each other. So when we talk about the different modulation mechanisms, OFDM does that. So what OFDM does, it creates multiple channels. And so I could communicate in one channel, and I will have that channel for myself, and another user will have another channel, and that problem will not be there. This is also the system that we use in cellular to avoid overlaps when we are using the same spectrum and at the same location. So those methods do exist, and they are implemented.
Okay, thank you.
Oh yeah, we'll tell you the story in a moment. There's one more question. It's a very good story. It's a funny one. We're a little bit over time, but I guess we...
Yeah, thank you for your lecture. I had a question regarding the last experiment. So you mentioned that you have an IMU on the receiver side. What's the reason for that?
Excellent question. So the question was that for this last experiment, where we need only one transmitter, I mentioned an IMU, which has a gyroscope, accelerometer, magnetometer. It's an inertial sensor unit. And without that, this would not work out. So your question is, why do I have it? Okay, I will not go into the math, but you see those two angles, the phi and the theta, the psi and the theta that are there? What happens is that, let's say that we are static. Let's say that you're the transmitter and I'm the receiver. And we will have this red line. So up to that point, I could not localize myself. Now, if I change for one angle, my light intensity will decrease, but I need to measure that change somehow. The IMU is the one that helps me measure that, the change in the angle, to have some idea. Without the IMU, I will not have that information, and I will not be able to solve mathematically the equations. So the way that you could see it is that this equation that you see there, we can have a series of equations for every single change in rotation that we have. Okay, you have a follow-up question, good.
Yeah, so I've been working with IMUs for like class practicals and so on, and they're very noisy. So how did you avert these issues?
You mean that the IMUs are very noisy?
The signals, yeah. If you had a newer IMU sensor, then it's fine. But with like long-term use, they start to get noisy.
Yeah, we cannot do much about it. So now that you're asking this detailed question, I guess what you may also know is that things like the compass, which is a combination of the accelerometer and the magnetometer, is not very good. But the gyroscope usually is pretty good for short-term things. So that's mainly what we use. But if your gyroscope starts failing, then It's kind of, the same thing will happen to a drone, by the way. If you damage the gyro, the drone will just start going crazy. So now we'll tell you the story. And it was about interference. This is wonderful because we designed this system. It was great. Kids can be very mean. Can we stop the recording now?
He will cut it out.
Okay. So we have these kids, right? And they really love it. And the demonstration was, you see like a superhero there with that light, I don't know the name. What we told the kids is, look, there's a flashlight, and put this flashlight, and the robot does not move. Now we have this special flashlight, it's like a superpower, and it will move. And we create sort of a competition where they have to move the robot from one location to the other. And what we noticed is that then two kids were going to compete, and at one point, one kid noticed that if it starts illuminating the other person's robots, it created interference, and the robot will not move. And so you saw these kids now starting to put the light on the other people, and then one of them also noticed that if it blocked the light, then there's no transmission. So they were using their hands and their bodies just to cover the transmission. Now, the good news about it is that for the kids, you let them play, and they start understanding because they see it, issues like interference, and you tell them, it's like two people talking at the same time. The good news was that high school students, when they saw that effect, they said, so how do you solve that for cellular networks? Right now my phones are here, and we have the same transmissions. And then you can start talking to them about just more advanced CDMA techniques and things like that. So it was a very interesting experience to give these systems just to younger people and see how they play. And you let them play, you let them discover these issues, and after that, you can start telling them how things work. And at the end, we told them, those radio systems that you have there is exactly what you have seen here in light. They are not dangerous. It's just that you cannot see those radio waves, right? So, but the funny story was just the kids trying to cheat on each other and do that. It's way over time. Thank you so much for your attention, and then maybe see you on Wednesday, okay?
Thank you.